Hi, chemistry students. We're looking at a video on colligative properties. So this should be pretty quick, but let's start from the beginning. All right, so colligative properties. All matter has these, but we're looking specifically at solutions. All right, so I'll explain what that means. So we've just learned about phase changes. We looked at heating curves, and I just want to go back to evaporation. Specifically, I'm going to use the term vapor pressure. All right, so water will just evaporate from the surface of a liquid. And so if we have like an open container of water, we'll get some evaporation steadily happening, and some water from the atmosphere will go back into the liquid phase. If we stopper it, what will eventually happen is we'll reach what we call the vapor pressure. So some water molecules leave the liquid phase and go into the gas. Some leave the gas phase and go into the liquid. This is not boiling, right? There's no bubbles happening. It's just evaporation, and it's an equilibrium, right? So see how in this picture there's 3 arrows going up, showing water from the liquid state becoming a gas, and 3 arrows going back down, showing how water in the gaseous state is going back and forming a liquid. All right, so all liquids do this. Liquids that do this more would be something like gasoline, right? That's why when you go to a gas station, you roll down the window, you get that very specific smell. Gasoline as a liquid is what's said to be very volatile, and that means it evaporates very easily, right? So you get more fumes essentially, all right? And it reaches, if it's a sealed container, if you have like a gas can in your garage or your backyard, you use it for your lawnmower or something, you may see it kind of puffs out like in the summer, all right? That's just these gaseous molecules bouncing around inside of the container, going back and forth from liquid and gas state. All right, so that's going to be important for colligative properties. But what we've been looking at so far has been pure substances. Every time we've talked about water, it was pure water. Well, today we're really looking at solutions, right? And I just want to remind you, a solution, it is the solvent. Water is going to be our solvent, and these solutes dissolved in it. All right, if you dissolve sugar in water, if you dissolve salt in water, if you were to dissolve potassium thiocyanate in water, that you don't have to worry about what that is though. All right, but things dissolved in water, you can have other things be your solvent, right? We can have acetone, we can have different solvents, but typically it'll be water. All right, so by having that solute dissolved in, it changes the properties of the liquid. All right, and it's going to change its boiling and freezing point. So again, what we're looking at is, yes, we're looking at water, but water with something dissolved in it. All right, so something that's spread out. You may remember we did the conductivity testers, right? So think about that. Things dissolved in the water. The sugar didn't conduct electricity, the salt did, but either of those count for today, right? Both of them are solutions. And one last thing I want to point out, we're not going to go into the concept of molarity. All right, we had seen that in school, molarity, moles per volume for a solution. I just want to use these two terms, concentrated and dilute. We know concentrated means we have a lot of the solute. We know dilute means not as much of the solute, right? So here, they're both the same type of thing. It's something blue being dissolved. The dilute one is a light blue. The more concentrated is a darker blue. We should feel comfortable with these terms, dilute and concentrated. All right, dilute means we have a lot of the solvent, a lot of the water. All right, think about like really watery iced tea. If you ever make it, doesn't taste good. Concentrated is very has a lot of the solute, maybe less of the solvent. All right, so that's like when you make that lemonade, it's way too sugary and it doesn't taste good. All right, so the solution changes the vapor pressure. And that's a very important concept. So normally a certain amount of water is able to leave the liquid state and go into the gaseous state, right? At a certain temperature, a certain amount can go. When the solute is in the solution, the water molecules are attracted to it. And since they're attracted to it, they don't want to leave the liquid state. So we see less water molecules leave the liquid state and become a gas, and less gas are able to rejoin, right? So you notice there are less arrows going up and down. The presence of that solute keeps the water in that liquid state better, and we're going to see that develop. All right, so colligative properties, a property of matter that depends on the concentration of the solution, right? So we're not looking at pure substances, we're looking at solutions. And there's two big colligative properties we are going to look at. There are more, but we're just doing two. The boiling point elevation and the freezing point depression. All right, so let's start with boiling point elevation. Think about that word elevation, we're going up. Boiling point, they say a watch pot never boils. All right, if any of you guys are helping with the cooking at home, think about making a pot of pasta. All right, you need to boil a pot of water, but what do you add to it? You add a little bit of salt. All right, you add the salt. Some people say you add the salt for flavor, but there's actually a science reason behind why you add the salt. All right, when you add salt to water, you no longer have pure water, you have a solution. And the presence of the salt in the water, it gives the water molecules something to be attracted to, so they resist boiling. So we get this boiling point elevation. When the water finally does come to a boil, it's at a higher temperature, all right? And then when you add the pasta to the water, all right, you're cooking the pasta. Heat is being transferred from the water to the pasta as it sits there. If the water is boiling at 100 degrees Celsius, all right, you're only able to transfer that much heat at a time. If the water is boiling at 105 degrees Celsius because you added the salt, now you're able to transfer more energy. Right? We saw with the heating curves that even if you add more energy, as long as it's still in the liquid phase, the temperature doesn't increase. All right, so cooking always has to do with the temperature. So adding the salt increases the boiling point, so you are actually able to cook quicker. All right, if you were to add sugar, that would also increase the temperature. All right, but it might kind of affect the taste. I know we were down the shore once and my grandma accidentally added sugar instead of salt, and her pasta just tasted off, and everyone was like, the water down here, it's different, you know, but it's fine. And we didn't realize the mistake till like the very end of the night. So, but again, it would also have the same effect. It would increase the temperature. All right, the boiling point elevation, it's an increase in the boiling point caused by that solute, right? So if water boils at 100 degrees Celsius, as you add more solute, you move it to 101, 102, 103, you know, up to like 110, let's say, right? It's not a huge difference, but it does elevate it. So it's something important. All right, and how that works, again, that solute gives the water molecules something to like attach to stay to, so they resist becoming a gas, right? When it's the pure water, they become a gas much easier. So that's why it boils at that lower temperature. All right, so just keep in mind, all right, friends keep you cool, all right? They make it harder to boil, which is why you need the higher boiling point, right? That's the presence of the solute. All right, now, in the wintertime, right, when it snows, when we get that ice, when it's super frigid outside, we need to use salt to make the road safe to drive on. One of the worst things you can experience is getting stuck driving behind a truck that is spreading salt, right? It just starts blasting your car. Terrible experience, all right? But anyway, this is due to the freezing point depression, all right? So it's kind of on the opposite side, all right? We elevate the boiling point. Now we can decrease the freezing point, right? So now water freezes at 32 degrees Fahrenheit, 0 degrees Celsius. All right. Now, it freezes at that temperature. It also melts at that temperature, right? So that's why, you know, like a refrigerator is usually around 36 degrees Fahrenheit. So if you were to put something with ice cubes in the refrigerator, they'll last long, but they will eventually melt because it's warmer. All right. Whereas your freezer might be, you know, 0 degrees Fahrenheit, you know, or maybe even like 10, depends. You can set it to different things. We put salt outside, we put it on our steps, we put it on the roads to lower the freezing point, but it's the same thing as lowering the melting point, right? So you don't have to salt the roads, you don't have to salt your steps if it snows overnight, but it's going to be 50 degrees during the day, right? Everything's just going to melt on its own. But let's say it snows in the winter and then the temperatures outside, it's predicted to be 20 degrees, right? The ice will not melt on its own at 20 degrees. But if you add the salt, you decrease or depress the freezing point, which is the same as decreasing the melting point. And now maybe it will start to melt. All right. And that's a good thing. That's why we want to use salt to melt the roads. All right. So the way it works, for a pure water to form ice, right, it has to kind of recombine, and then the ice just has to spread out to undo itself. Well, if we have salt water, those salt particles get in the way of the water molecules, and they make it hard for the water to form that solid ice. So they almost have to push them out, which just adds this extra process. We get like this slush, and that slows down the freezing point. Now, if we have ice and we add the salt, it starts to kind of work its way in till we get that slush. All right, so that's, I think, the worst part of a snowstorm, when you have that real nasty slush that's about everywhere until it finally melts and goes away. All right, I like the nice snow. I don't like the slush, but that is this extra step that the solute adds, which causes the freezing point to decrease. All right, so friends keep you from freezing. So these solutions, the solute in the pure water, these solutions typically want to stay in the liquid phase, which is why we get the higher boiling point and the lower freezing point. All right. Now, if we were in school, we would be using this opportunity with colligative properties to make our own ice cream. All right, because we can add ice cream salt to ice, and it will melt at a really low temperature. It'll get really cold, and you can actually pull the energy from something near it. If you were to put salt and ice on your skin, please do not try that at home. It would burn you. But if you had a little plastic bag of sugar and milk and some vanilla or some chocolate, you would actually pull the energy with that rock salt ice mixture, and you would make your own ice cream. So it's a lab. If we come back to school at the end of this year, we'll definitely make ice cream one day. All right, so just again, boiling point goes up, freezing point goes down when we have a solution. All right, and something I want to point out, salts are better for colligative properties because they separate to form 2 or more particles per compound. So if you have NaCl, when one NaCl compound dissolves in water, you get an Na plus ion and a Cl minus ion. So it's almost like it becomes 2 particles in the solution. Whereas like when a sugar molecule dissolves, one sugar molecule gives you 1 particle in the solution. So remember when we would make the puzzle pieces for ionic compounds? If these were to dissolve in water, you would get as many particles as there were puzzle pieces. So this would be 3 solute particles, this would be 2 solute particles, 3, this would be 5, 4 over here, and this would be 2, right? Ionic compounds, they separate, and that's a good thing for colligative properties because it counts as more particles, so it's almost like it's more concentrated. All right, so this would be like a classic type of question I would ask you on intermolecular forces. What would boil at the highest temperature? Dilute sugar water, dilute salt water, concentrated sugar water, concentrated salt water, or pure water. All right, boiling at the highest temperature. Pure water is actually going to have the lowest boiling point. All of these other 4 have something present, so those colligative properties elevate the boiling point. All right, concentrated is going to be better than dilute, and salt is going to be better than sugar because salt is going to separate into multiple pieces. So for this question, the choice would be D, concentrated salt water. All right, now, so colligative properties help water boil at a higher temperature, but can it ever boil at a lower temperature? Well, yes, it can. All right, did you know water boils at a lower temperature in the mountains than at the beach? So just a reminder, boiling has to do with the atmospheric pressure. All right, now we're pretty close to sea level, so we don't have a big change. Water boils at 100 degrees Celsius at sea level. As you go higher up, so Pikes Peak in Colorado, it's 4,400 meters above sea level. Water boils at 85 degrees Celsius. All right, and on Mount Everest in Tibet, which is twice that height, 8,800 meters, water boils at 71 degrees Celsius. All right, and that's an issue. It makes it hard to cook food on Mount Everest because remember what we said with the pasta? Cooking is a heat transfer. So you can't transfer that much heat if you're only at 71 degrees Celsius. We like to cook at around 100 degrees. Right? So that's going to be an issue for people up on Mount Everest. All right. So let's watch this video on boiling.
Investigating wildlife in the Andes Mountains, Darwin noticed something that plagues all mountaineers who try to boil potatoes. They take ages to cook. Darwin put it down to altitude, and it was right.
So it takes longer to cook.
We learn that water boils at 100 degrees C. But as Darwin noticed, the boiling point varies if you're at the mountain.
Now I'm just going to skip ahead a little bit in it. But what they're using in this video is a vacuum pump. And so what they're going to do is they're going to lower the atmospheric pressure on it. So as they lower it, the water will eventually boil. So they have the marshmallow there just to show the marshmallows expand. We'll talk about that next week. But we want to just watch what happens to the cup. All right, he's in a really cold room, and you'll see it like shake a little bit and then all of a sudden boil. At my old school, I had one of these vacuum pumps and it did work really well. The ones we have at Old Bridge, unfortunately, don't work very well. All right, but you see it like begin to shake for a few seconds and then out of nowhere, it just starts going. Yeah. And now it's completely boiling over. And that's just by placing the water in a vacuum chamber and reducing the atmospheric pressure. They're not adding any temperature. All right, but it boils on its own. All right, so we'll move on. So one last thing I want you to see in this video. We call it a phase diagram. A phase diagram includes pressure and temperature. All right, now the normal freezing point and the normal boiling point are both at a pressure of 1 atmosphere. All right, so this is the phase diagram for water. And at 1 atmosphere, as we add heat, we go from solid to this section's liquid, we freeze, excuse me, and then we boil and we go from liquid to gas. All right, we have something called the triple point, which is where all 3 phases of matter are present at the same time. It's very weird. I have a video on that. And we have something called the critical point. And the critical point is a point where at a higher pressure or a higher temperature, we cannot distinguish the difference between a liquid and a gas. All right, if you've ever heard of supercritical liquids or supercritical fluids, that's at that critical point. Those are things done in labs at super high temperature and at high pressure. All right, so again, this is the phase diagram for water. Right, it's always solid on the left, liquid in the middle, and gas on the right. All right, and the colligative properties are in blue, the solution. The pink represents the pure solution, and what the presence of the colligative properties does is it lowers both, so that's why we get a lower freezing point and a higher boiling point. It like spreads it out in both directions, which I think is pretty interesting. All right, this is the phase diagram for carbon dioxide. All right, you may know carbon dioxide as dry ice. And at 1 atmosphere, right, that's a very normal atmospheric pressure. It goes straight from solid to gas. That's why dry ice, it sublimates. And I'm still looking forward when I get some dry ice. I'm going to film some videos with it because there's a lot of cool stuff, the way that it just goes straight from solid to gas. But it goes from solid to gas at negative 78 degrees Celsius, which is why if you have dry ice in a cooler, you can keep things cold for a pretty long time because as it's sublimating, it's happening at a really low temperature. So that's why they're able to ship frozen things around the country, like steaks, in a cooler with dry ice. All right. So again, this is just going to highlight the 4 points I want you to know on a phase diagram. Normal boiling point, that's the boiling of a substance at 1 atm of pressure. Normal freezing point, freezing at 1 atm of pressure. Triple point, it's where the 3 lines converge, and it's where the substance is in all 3 phases of matter at once. It will move spontaneously between those 3 phases. All right, something very difficult to achieve. Typically, can only be done in a lab if we can control the pressure. And the critical point where we can no longer distinguish between a liquid and a gas. So this is the last thing I have for you guys. Actually, I have one more thing. So this is a substance in a lab. They're manipulating the pressure and the temperature. And so they get it to the triple point. So we see the liquid right now. It's going to crystallize. We can kind of see, right? So it crystallizes over. That's it freezing. It just turned from a liquid to a solid, and then we see it start to crack already. It'll melt and it'll start to boil, all happening spontaneously. They're not changing anything. They got it at the right pressure and the right temperature. They just leave it alone now. So now we see it's boiling a little bit. Now it's refreezing. It just goes back and forth. When you're at the triple point, it can be in any one of those states at any given moment, right? It has no preference, and it spontaneously just changes. So it's bubbling, and it's frozen, and it's liquid. So it's some pretty crazy stuff. And I do have one last thing I wanted to show. All right, so going back to Everest, how do they cook on those mountains? All right, they use something called a pressure cooker. All right, a pressure cooker, like the Instant Pot, is the really popular one right now. A pressure cooker is sealed, and it allows steam to build up, so that as you get more and more steam inside the pressure cooker, you always have to start with some amount of water. As you get more and more steam, you get more of these particles. It builds its own pressure inside the pressure cooker, and as a result, it can get water boiling at like 130, 140 degrees Celsius. Since it's so high, it's able to transfer heat quicker, so you're able to cook things pretty quickly. All right. If we were in school, this would be the moment where I would bring in my own Instant Pot, and I would fill it with chicken and barbecue sauce at the start of the period on a lab day. And by the end of the period, it would be done. It would have already cooked, and we would have like pulled chicken, and we would have those sandwiches as you walk down. It'd be a good time. All right. But if any of you guys have a pressure cooker at home, you know that you have to very carefully vent it when it's done. You get a lot of the steam that comes out. And the whole point is the pressure cooker is building pressure to increase the boiling point, like we saw on these phase diagrams. As the pressure goes up, we're on this line, the boiling point increases. We're able to transfer more heat. So that's everything you need to know about colligative properties. All right, so you want to finish the worksheet on that, and we'll be good for this week.